When panel A feeds panel B with a 208/120 volts, three-phase, Y-connected system, and you're sending the three phases plus neutral to panel B, which primarily powers 120 volts nonlinear circuits, the question arises whether the neutral counts as a conductor and if the wires in the conduit feeding panel B need to be derated. Also, it's important to understand when derating is specifically needed for the neutral wire, especially when the neutral current isn't always traveling in the opposite direction of the phase conductors. Yes, the neutral counts as a conductor in the scenario. Now, regarding whether the wire in the conduit feeding panel B must be derated, it depends on the type of load and the wiring method used. For linear loads, such as incandescent lights or resistive heaters, the neutral wire typically doesn't carry any unbalanced current. As a result, it usually does not need to be derated. However, for nonlinear loads like electronic devices or variable frequency drives, things are different. Nonlinear loads can cause current harmonic distortion, which can significantly increase the neutral current. In this case, the neutral wire may indeed need to be derated. It is imperative to consult the applicable electrical code requirements for precise guidelines. Derating of the neutral wire is required when the unbalanced current in the neutral exceeds the ampacity of the wire. This situation can occur under several conditions. Firstly, if the load is unbalanced, meaning more current is flowing in one phase than the others, it creates an imbalance that the neutral wire must carry. Secondly, if the load is nonlinear, it introduces harmonic distortion into the electrical system, leading to increased current in the neutral wire. Thirdly, if the conduit contains more than 3 current-carrying conductors all traveling in the same direction, this also necessitates derating. In the scenario presented, where panel B is mostly made up of 120 volts nonlinear circuits, the neutral wire is likely to carry unbalanced current due to harmonic distortion. Consequently, the wire in the conduit feeding panel B should be derated according to the relevant electrical code requirements. It's important to clarify a common misconception. The neutral current does not always flow in the opposite direction of the phase conductors. In some cases, particularly for balanced linear loads, the neutral current may flow in the same direction as the phase conductors, or it may be negligible. To delve deeper into this topic, let's first define linear and nonlinear loads. A linear load is one in which the current is directly proportional to the voltage. Examples include resistive heating elements and incandescent light bulbs. In a balanced three-phase system with linear loads, the neutral current is ideally zero because the currents in the three phases cancel each other out. A nonlinear load, on the other hand, is one in which the current is not directly proportional to the voltage. This category includes electronic devices such as computers, LED lighting, and variable frequency drives. These devices draw current in short pulses, which distorts the sinusoidal waveform and introduces harmonics into the system. Harmonics are multiples of the fundamental frequency, which is typically 60 Hz. The third harmonic, which is 180 Hz, is particularly significant in three-phase systems with nonlinear loads. The third harmonic currents in each phase are additive in the neutral conductor. This means that the neutral conductor can carry a current that is greater than the current in any of the phase conductors. Now let's discuss the National Electrical Code (NEC) requirements for neutral conductors. The NEC provides guidelines for the sizing and derating of neutral conductors in various situations. According to NEC section 310.15, the ampacity of a conductor is the maximum current, in amps, that the conductor can carry continuously under the conditions of use without exceeding its temperature rating. Several factors can affect the ampacity of a conductor, including the ambient temperature, the number of conductors in a raceway or cable, and the type of insulation. When determining the ampacity of a neutral conductor, it's essential to consider whether the load is linear or nonlinear. For linear loads, the neutral conductor is generally not required to be larger than the phase conductors. However, for nonlinear loads, the NEC requires that the neutral conductor be sized to carry the maximum unbalanced load, which can include harmonic currents. Specifically, NEC section 220.61 provides requirements for sizing the neutral conductor in a service or feeder. This section states that the neutral conductor must have sufficient ampacity to carry the maximum unbalanced load. In a three-phase, four-wire system, the maximum unbalanced load is the maximum net calculated load between the neutral and any one-phase conductor. Furthermore, in EC section 310.15 B3 states that a neutral conductor that carries only the unbalanced current from other conductors of the same circuit is not counted as a current carrying conductor when applying the ampacity adjustment factors in NEC section 310.15 B3. However, this exception does not apply if the neutral conductor carries a significant amount of harmonic current. If the neutral conductor carries a significant amount of harmonic current, it must be counted as a current carrying conductor when applying the ampacity adjustment factors. The NEC does not provide a specific definition of what constitutes a significant amount of harmonic current. However, as a general rule, if the harmonic current in the neutral conductor is greater than 10% of the fundamental current, it should be considered significant. When derating conductors due to the number of current-carrying conductors in a raceway or cable, it's crucial to consider the neutral conductor. If the neutral conductor is carrying only the unbalanced current from linear loads, it does not need to be counted as a current-carrying conductor for derating purposes. However, if the neutral conductor is carrying a significant amount of harmonic current, it must be counted as a current-carrying conductor. To determine whether the neutral conductor needs to be derated, it's necessary to calculate the expected current in the neutral conductor. This calculation should take into account both the unbalanced load and the harmonic currents. The unbalanced load can be calculated by determining the maximum difference in current between any two phases. The harmonic currents can be estimated based on the type and quantity of nonlinear loads connected to the system. If the calculated current in the neutral conductor exceeds the ampacity of the conductor must be derated. The derating factor is determined based on the number of current-carrying conductors in the raceway or cable, as specified in NEC section 310.15 B3. In some cases, it may be necessary to increase the size of the neutral conductor to avoid derating. Alternatively, it may be possible to reduce the harmonic currents by using harmonic filters or other mitigation techniques. In addition to the NEC requirements, local codes and regulations may also apply. It's essential to consult with a qualified electrical engineer or inspector to ensure that the neutral conductor is properly sized and derated for the specific application. Let's consider a practical example. Suppose you have a 208/120 volts, three-phase, four-wire system that is supplying power to a panel board. The panel board is primarily feeding nonlinear loads such as computers and LED lighting. The total load on the panel board is 100 amps per phase. To determine whether the neutral conductor needs to be derated, you need to calculate the expected current in the neutral conductor. First, calculate the unbalanced load. In this case, let's assume that the maximum difference in current between any two phases is 20 amps. Next, estimate the harmonic currents. Based on the type and quantity of nonlinear loads, let's assume that the harmonic current in the neutral conductor is 30 amps. The total current in the neutral conductor is the sum of the unbalanced load and the harmonic currents, which is 20 amps plus 30 amps, or 50 amps. If the neutral conductor is a number 6 American wire gauge (AUG) copper conductor with a temperature rating of 75 degrees Celsius, its ampacity is 55 amps. In this case, the calculated current in the neutral conductor is less than its ampacity, so derating is not required. However, if the neutral conductor were a number 8 AWG copper conductor with a temperature rating of 75 degrees Celsius, its ampacity would be 40 amps. In this case, the calculated current in the neutral conductor exceeds its ampacity, so derating would be required. To comply with the NEC, you would need to either increase the size of the neutral conductor or reduce the harmonic currents. In summary, the neutral conductor counts as a conductor and may need to be derated when feeding panel boards with nonlinear loads. The derating requirements depend on the type of load, the wiring method, and the applicable electrical code requirements. It's essential to carefully consider the unbalanced load and the harmonic currents when determining the appropriate size and derating of the neutral conductor. This ensures a safe and reliable electrical system. Remember that the information provided here is for general guidance only and should not be considered a substitute for professional electrical engineering advice. Always consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and regulations. The NEC is updated regularly, so it's important to stay current with the latest requirements. The NEC is a comprehensive document that covers a wide range of electrical topics. It's essential to have a thorough understanding of the NEC to ensure the safety and reliability of electrical systems. In addition to the NEC, there may be other applicable standards and regulations, such as those issued by the Institute of Electrical and Electronics Engineers, IEE, or the National Fire Protection Association, NFPA. These standards provide additional guidance on specific electrical topics, such as power quality and grounding. It's important to be aware of all applicable standards and regulations and to follow them carefully. Proper grounding is essential for electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to trip circuit breakers and prevent electrical shock. The NEC provides detailed requirements for grounding electrical systems. It's important to follow these requirements carefully to ensure that the system is properly grounded. Surge protection is another important aspect of electrical safety. Surges are transient overvoltages that can damage electrical equipment. Surge protection devices, SPDs, are designed to protect electrical equipment from surges. The NEC provides requirements for the installation of SPD. Power quality is an important consideration for sensitive electronic equipment. Poor power quality can cause equipment to malfunction or fail. There are several factors that can affect power quality, including voltage sags, voltage swells, and harmonic distortion. Power quality problems can be mitigated by using power conditioning equipment, such as uninterruptible power supplies, UPSs, and harmonic filters. Electrical safety is paramount. Always follow safe work practices when working with electricity. Wear appropriate personal protective equipment, PPE, such as gloves and safety glasses. Energize circuits before working on them whenever possible. If you're not qualified to work on electrical equipment, hire a qualified electrician. Electricity can be dangerous, but it can be used safely if you follow the proper precautions. Staying informed, adhering to codes and standards, and prioritizing safety will contribute to a reliable and secure electrical system.